So we've looked at how to another method for solving first order differential equations. So that was the integrating factor method that we did last time. Now we're moving on to solving second order differential equations. So we're going to start off by solving second order differential equations that are equal to 0. That's what homogeneous means. It means it's equal to 0. And we're going to look at next lesson solving non-homogeneous differential equation. Okay. The second order means it includes a second derivative of d squared y by dx squared. It can include dy by dx's, and it might have a y in there as well. So these ones need to be in this form, so it can't be like y squared and stuff. It needs to just be y and things like that. This is one of those things where you just learn the method and don't think about it too hard. It just works. Okay. So what we're going to do is for our second order differential equations is we first write down what we call the auxiliary equation, okay, which is a quadratic equation with the same coefficients as your second derivative and your first derivative and your y. Okay. Now they use m in the pack. I got taught lambda, so I'm going to use lambda, but they're the same thing. Depending on your how many solutions your quadratic has will depend on what the form of your general solution is. So you need to learn these 3 separate cases for if there's 2 real solutions, if there's a repeated solution, or if there are 2 complex solutions. There's 3 different cases that you need to learn. Okay. So let's have a look at this example one first here. So this is our second order homogeneous differential equation. First thing we're going to do is write down the auxiliary equation. I'm just going to do that with AE. So the auxiliary equation for this one, I'm going to use lambda instead of dy by dx and dy by dx squared. It's just got the same coefficients as that. So this is lambda squared minus 2 lambda minus 8. This will factorize, or you can follow it in your calculator. And we'll give you 2 values for lambda, 4 and minus 2. So we get 2 real solutions for this one. If you get 2 real solutions from your auxiliary equation, your general solution to this differential equation is of the form a e to the 4x plus b e to the minus 2x. So you've got 2 arbitrary constants because it's a second order differential equation. You know, first order differential equations just have 1 constant, usually plus c or whatever. This is a second order one, so it's got 2, and it will be e to the power of one of your roots x plus b e to the power of your other root times x. Okay, and just accept that it is. You could differentiate to justify it to yourself that it will give you the same. It is a solution. But just learn that that's the form if you have 2 real roots. Yes.
It wouldn't matter if you do like b or x.
No, if you swap to the 2 and the 4 and the minus 2, then that's fine. Yeah. Okay. Can you quickly do the U chart, please? Then just differently. Okay, so your auxiliary equation this time, 2 lambda squared minus lambda minus 3 equals 0. If you solve that, you get 2 solutions, 0, 2, and minus 1. So you get a e to the 3 over 2x plus b e to the minus x, or the other way around this. So that's the first type that you might get where you get 2 distinct real roots. Now, if instead you get a repeated root from your auxiliary equation, this won't work anymore because you need there to be 2 different constants, your a and your b. But if you put the same value in, you'd just be able to combine this together into a single constant. So we need a different approach if you get if you get a repeated real root, which is to put it in this form. So you do e to the power of your root times x. And then instead of like a times one of those and b times one of those, you have ax and again, just learn that form. So for this one, if we write down the auxiliary equation, you get 4 lambda squared plus 4 lambda plus 1, which if you solve this, you get lambda is minus ½ as a repeated root. That means that your general solution to this equation is e to the minus ½ x. And then times ax plus b, because it doesn't make sense to put a e to the minus half x plus b e to the minus half x. Because they're the same, you just combine those together. Okay. And again, you just accept that this does work. You could justify it to yourself by differentiating it and substituting it in.
For your auxiliary equation, you get repeated root 3. So your general solution is y equals e to 3x times a.
Third type of equation is if you get complex roots for your auxiliary equation. So again, you just accept that this works. So if you get complex roots for your equation, well, yeah, if you get complex roots for your equation, you just get this form. So you get e to the real part times x, and then you get a cos of the imaginary part x plus b sine of the imaginary part x. It's kind of because of something that we're going to learn in the second complex numbers pack. Because if you did it like case A, the first one, it kind of is right. So if you put the complex bits in as power of e here, that's right. But in the complex pack, we're going to do that e to the I theta is cos theta plus I sine theta, which is kind of where this comes from. Okay. But again, it's just another form to learn here. So we've got here our second order differential equation. So our auxiliary equation is lambda squared minus 2 lambda plus 5 equals 0. You can solve this on your calculator if it's in complex mode. Bless you. Fine. Mine's not in complex mode, so shift set up complex mode. A plus I. And you get two solutions, one plus or minus 2i. This means that your general solution is y equals e to the real part times x. So that's e to the 1x. E to the x. And then inside the brackets, you get a cos 2x plus b sine 2x. You don't need to worry about the plus or minus. It's just the value of the imaginary.
Okay, so we solve this, you get plus or minus for I. So the real part is 0, e to the 0 is just 1. And you just get a cos 4x plus b sine 4x.